Hi guys, welcome to another LER Electronics repair video. Here we have a graphics card from a subscriber. Actually two of them together, so this was Alvaro and Luis, who live in Las Palmas, Gran Canaria, and they brought me 5 GPUs to look at. This is the second of them. This has a very interesting backstory. So let's see what's in the box and let's see what it says. So this is an RX480 and you can read it. So they sold this on eBay as a working GPU, and the buyer then claimed it did not work and sent it back, so they were forced to refund him. And when they got it back, it has no picture. Yeah. And I said, you know, guys, whether I can fix this or not, it's going to be really interesting to find out what you've got back and why it doesn't work. Okay, so let's have a look at it. Quite nice chunky thing, really. Sapphire Nitro dual BIOS RX480. And it's been put, oh yeah, and some screws missing, but I can't say if the screws are missing because that's how it came back from eBay, or whether I know Alvaro and Luis have had a look at these cards. So the first thing we're going to do with this then is to remove the heatsink, remove the backing plate, and let's see what we have. So the first thing I noticed then is that the fan isn't connected, but again, this could be Luis and Alvaro have looked at this. Corrosion in the heatsink again, but this is very normal for cars you'll find on Gran Canaria, due to being in close proximity to the Atlantic Ocean. I mean, you can get 13 miles away from it, the furthest on the island. Okay, so that may not really mean anything. Let's go a little bit further and let's get the heatsink off, and let's now see what we have here. I could have paused and done this, but I think it's better. Oops. Oh, I hope that was okay. I hope it's. I think it's better for dramatic effect. Yeah, to do this on camera. Okay. And there we have it. Plenty of heatsink compound and one graphics card. So we'll do the normal. First thing, let's have a quick look around under the microscope for any obvious damage, and then let's see what we have in the way of resistances on this. Quick look around the GPU side there, just looking for obviously broken or burnt components on this. Nothing standing out. Bit of fluff and stuff on it, but that's not anything I would particularly be concerned about. No signs of particularly of like somebody butchering this or repairing it or whatever. RAM chips look very typical for RAM chips off a mining card. This is an ex-mining card. Everything looks sort of okay. This, heatsink compound everywhere, but you know, that isn't unusual either. It's kind of all over the place, okay, but I doubt that would cause no picture. You can see that he's been running quite hard. This is what you get when you buy ex-mining cards, guys, just so that you know. Not saying they won't work just fine, just showing you what you're getting. Drivers, the IR3553M is very common ones. In fact, I have some of these in stock. I bought 10 for a previous repair that just needed 1. Seems like it was a good idea. Yeah, so it's alright. I see some fuses and things. Let's have a quick look on the last bit. Yeah. That looks okay. The other side, because there's a backing plate on this, I'd be surprised if there's any physical damage to it, but let's have a look. Otherwise, knocked off components and such like. By knocked off, I don't mean like fake. I mean knocked off, like broken off. Yeah. I don't mean like knockoffs. If you, yeah, you know what I meant. Let's see. I amuse myself if I didn't amuse any of you guys. Yeah. Just stuck on the edge of the mat. All looking quite reasonable, but was this heatsink compound? Yeah, how you've got this everywhere, guys? I don't know. How do you do that? You know, how do you get this stuff everywhere like this? Just the focus a little bit, because I'm moving across the board, so it's getting higher because of the bracket. Nothing standing out that would be a problem. Yeah, focus up again. See. Yeah, that looks okay. Oh, if you guys are interested, I know some of you asking about microscopes. I got an email from Andon Store just before the weekend, and they're sending me one of their latest USB microscopes. Asked me if I will have a look at it and make a short video. So although I'm not a great user of USB microscopes, and I think a lot of you guys know why, I'm going to be having a look at one of their new ones, so I think you might find that interesting. Yeah. Anyway, that looks okay to me. So next thing then, let's have a look at some resistances, and as soon as I have the microscope to hand, let's look at the ones on the PCIe lanes first down here. First of all, 12 volts, because we just happen to be by the 12 volts connector, so why not? No short on 12. Fourth one in. What's that reading? Oh, that's low. That's low. 11.2 on the 3.3 volts. That ain't normal. Okay, so we found something there. First three here, of course, are going to be all 12 volts, and they're just fine. Okay, so this is the first PCIe lane on this side of the board. No moment before we panic. Diode mode. Okay, so this is the first PCIe. Do you see how that reads rock steady, by the way? And this one, Albert and Lewis, this is for you. I'm just going to show you what's wrong with your with your RTX 2060. One moment, guys. This is your RTX 2060. Looked at a couple of videos ago, and this is the same on the point on this one. So the first PCIe lane, and I have a look to see what happens on it. I know you've probably seen it before. I don't know what was. You see that? That isn't normal. I know you said you thought this had been connected to a mining adapter the wrong way round and sent 3.3 volts down here, and I'd say you're probably right. I think there's a short inside this GPU from here to one of the power rails, probably. And I'm seeing the capacitors on the power rails charging up. I'm not sure for certain, but I'm pretty certain, unless somebody's going to tell me different, this one is not repairable. This is the one that had the welded on short circuit high side MOSFET here. This is my attempts to try and be unsoldered as welded. So apart from using this as an experiment to see if we can remove this, and then maybe that strange climbing reading might go away. But if it doesn't, then this, I'm sure, is one that can't be repaired. Anyway, back to where we were. So the first PCIe lane looks okay. Yeah, see the difference? Okay. And we go to the other side of the board, and then we can look at the ref clock. So that's this side. I'll just get it into focus. Okay. Ground, finally got ground point. Okay. and ref clock on pins 3 and 4. Sorry, pins 2 and 3. You can see them here. 813, 813, and they won't be shorted to each other, and that's reading about right. I mean, the other one, if you look at it, of interest, this is your RTX 2060, pins 2 and 3. Again, we'll just go, and on this one we have, yeah, see, 798 close, yeah. Okay. So far, I can see there's a bit of crap on the PCIe, but I'm not worried about that. This has a problem on the 3.3 volts rail. But it's practically short on diode mode, and it was about 20 ohms, I think. 1, 2, 3, 17, 11 ohms. Okay, let's have a look at the other resistances on the board. We'll start with 12 volts coming in. Which side's grounded the connector? Is it this side? No, it's the other side's ground. Yeah. Okay, so there's no short on 12 volts. We have 2 fuses here, so we'll check both sides. So this is the side that goes to the 12 volts, and this is the other side of the fuse. And there's no shorts on 12 volts. Okay. This coil will be a filter on 12 volts coming in, and probably this one down here will be a filter on this 12 volts coming in here as well. Wouldn't surprise me. We have a buck coil here, no short. Well, we'll test this one. No short. Does that actually go to the 12 volts? I'm interested. Yeah, filter on 12 volts coming in. We have this one which looks different from the others, so this will be the RAM phase, and probably the easiest way is to go onto the junction between the MOSFETs. I'll zoom down on the overhead camera actually. So you can see the MOSFETs, and if you've watched the previous videos, the singleton is the high side MOSFET and the two together are the low sides, and the drain of the low sides, the two together, will be going to the RAM, and that's reading me 19 ohms, but I don't know what the reading should be on these cards. What memory is it? Samsung memory. Yeah, Samsung memory, that reads fairly low actually, but we'll say probably that is okay. We then have these 4 together and 1 separate. So it might be these 4 are V-core and this is something else, maybe memory controller. So let's flick it over, let's have a look, see what we've got. So we have, I'll just get onto the coil. Oh, the surface mount, are they? Yeah, the surface mount coils. Okay, easy. So this one, 1.2, looks quite reasonable for the core. 1.2, these will all be the same because these are all on the V-core. One that isn't fitted, what's this one? Okay, so actually all 5 phases seem to be on V-core. This seems to be possibly V-RAM, but we have another one here that could be, this could be V-memory controller, 12 ohms. $19 ohms, could be memory controller. If this one reads a bit higher, so what's this one reading? Again, I can't get to the coil because it's not a surface mount, but these are the 2 low sides and this is the drain. Just get a good connection onto ground. Oh, that's quite high. Maybe I have a bad connection. I'll just try. This side should be ground. Oh, that's interesting. That's interesting, guys. This side should go to 12 volts somewhere. Either up here or over here. Yeah, over here. That's 12 volts coming in. So this then should be connected. The source of the high side and the drains of the low side should connect together. And then from here to ground, we should see the resistance of the load. Oh, I had a bad connection. 30 ohms. That I'm pretty sure is VRAM, and I think that's okay for Samsung. So that's looking okay. This one, this is going to be PEX, 35 ohms. Quite probably PEX. Another fuse here. Looks good. Just check around a few of these low value resistors, these current sense resistors. That's looking good. Don't see any more. Oh, I see a voltage regulator here. What's this one? Oh, it's high. That is quite high. That is quite high. This is probably the 5-volt regulator, so probably if 12 volts is coming in here and going to this thing, yeah, 12 volts in, 5 volts. That's your 5-volt regulator. So the main thing we can see with this, without a doubt, is that we have a short circuit on the 3.3. Well, not short, but we have an unusually low resistance there. I don't believe that's normal. Let's see if we can figure out where that actually goes to. First thing I'll just try is there a board view or a schematic for this card? I don't have a board view, but I do have some schematics, and this I think is the reference card, the AMD schematic. Okay, and this shows us straight away, this is your PCIe slot, and you can see that the 3.3 volt comes into this signal 3.3V bus, and also from the other side of the board here. So if we have a look to see where this signal goes to, it can give us some idea, obviously, what's connected to here. Now, I'm sure that this is going to go to the BIOS chip and it's going to go to the GPU. I'm not sure where else it might go to, but it probably goes quite a few places. Probably uses a pull-up signal for logic, or even a supply for some of the chips that run on 3.3, which I'm sure there will be. But let's have a look. So 3.3V bus. You know, it's on it anyway. VUS. So I'll just Control F to search for that. So we can see it comes into some chip. Firmware. This is the BIOS. So it goes to the BIOS. We can see that. Okay. This is like a pull up to resistors. It goes to the GPU. This is part of the GPU. So it supplies a GPU, which we'd expect if it's supplying the BIOS. The GPU must have 3.3 volt supply. If it's a 3.3 volt BIOS, it has to have. Just as a pull up here, just a pull up here, just a pull up. So the only place we can have short so far are in the BIOS chip or the GPU. Yeah, it's just a pull up, it's just a pull up, and we're back to the BIOS. Okay, so that is literally where it goes to. We could see on the schematic or similar schematic that the 3.3 goes to the BIOS, and I'm sure that's the case on our board. Yes, it goes to the BIOS. We know it goes to the GPU or part of the GPU, and I'm pretty sure we can measure that. If we look on the little capacitors on the GPU, I can probably find one that's on the 3.3 volts. I've cleaned off all the heatsink compound from the GPU, and it actually looks okay. I don't see any problem with it. We can have a quick look under the microscope. And I can't actually see any of the capacitors on here that are connected to the 3.3, but I do know from the schematic, which you've just seen, that it does go here. Probably there's no capacitors actually on the die. I suspect if I went around all these capacitors underneath, I will find the 3.3. So given this is not a short, it's like 12 ohms, at 3 volts, roughly speaking, if we put 3 volt supply on here with about 12 ohms, we will see 250 milliamps of supply. It's easy to work it out. 3 ohms at 3 volts is 1 amp. Yeah, so therefore 12 ohms is about a quarter of that. Yeah, I mean, given the fact it's 3.3 and it's a bit less than 12, so it's probably more like 300 milliamps. So I'm going to power this up and see which voltage rails I have, and see if we can work out why we have such a low resistance on the 3.3. But I suspect it's probably the GPU, because I don't think it's the BIOS chip, and it doesn't really go anywhere else. So let's power this up. We know it's not going to have a short as such. Let's just see what it actually does. So I'll just first check to see if the GPU is getting warm. So it's powered up, and I don't feel anything hot. I got one bleep out of it, but that's probably the onboard graphics. But this is cold, so it's obviously not running. Oh, and then the computer switched off again, and it switched it back on again. So the computer switches off and on, but not like there's a short, just like it wasn't happy with something. Yeah, definitely no power. Let's see what we've got. So we have 12 volts coming in. 12 volts. I'm pretty sure this is the 5 volt regulator, which is the next rail to come up. Oh, the computer's still on. There's 5. 3.8, that's a bit low. It's on the other pin. Yeah, it is 5. Computer shut itself down again. Stayed off. So the computer's kind of like shutting itself down effectively. What else we got? 0.9, that's probably PEX. Some VCore. No VCore. Still cold, obviously. VRAM. No VRAM. Can we find the 3.3 volts on the BIOS? Is it this pen? There's your 3.3. So 3.3 is steady. So we've got PEX, we've got 3.3, we must have 1.8 if we got PEX, I'm just not sure where it is. What's this one? That's not running, doesn't surprise me. Okay, so basically it's working as far as we have PEX. So the next thing then, if this is an AMD card, is probably going to be VRAM. So I think we need to have a look through all the various voltage rails on this and see if we can figure out where the power goods are. So I'm looking for power goods coming out of the controller on PEX. Let's see if it's good and then let's see where it goes to. I'll just show you now the power sequence diagram for this graphics card so that you can understand the process of fault finding that we're going to go through. Here is a power sequence diagram for NVIDIA cards 1000 to 3000 series, and you'll see here we have the RX400 and 500 series, which is ours. This is showing you which voltages are applied on what order to start the card up. So this is in time. This is, if you like, starting from when you first switch on, and a process which may only take some milliseconds, not very long, but each step comes one after the other. So you can see the first thing that happens is the 12 volts comes on and the 3.3 volts comes on. These are coming from the computer. Once we've got these two, the 5 volt regulator on the graphics card comes on, and we know that's working. We can see we have 5 volts. Once these three are all present at this point, yeah, all three are present, the signal 1.8 volt enable goes to the 1.8 volt regulator. Now I've not found this regulator, but I do know it's working, and this is why. The 1.8 volts must come on before the PEX can come on. So 1.8 generates the signal 1.8 volt power good. That goes to the controller for the PEX voltage rail, the 0.9, and that switches on. And we know we have that. We can see that. We can see 5, we can see 0.9, and we must have 1.8 somewhere. The next thing that should happen after that is that the memory voltage rail should power up, MVDD, and we don't have any VRAM. So the obvious way to fault find this is to start from PEX power good, see if that signal is there, and then trace that to the controller for MVDD. So power good here will come to enable there, and this is where we need to look now. What's happening to the signal between the controller for PEX and the controller for the memory voltage supply? We know the power sequence, so we know that 1.8 volt comes on before the 0.8 volts. And we can see here this schematic, which may or may not be the same as our card. We have 1.8 volt power OK, and via a couple of transistors it generates 0.8 volts enable. So this must go to whatever chip is generating the PEC supply 0.8, which we have. So if we just search for that, so I hit Control F and just typed in here what I want to search with, sorry, what I want to search for, and I'll have a quick flick through, and yeah, okay, that looks like a chip. So we can see here 0.8 volt enable comes into a chip. This then, this is the buck converter, so here's the coil we can see. This is your 0.8 volt supply, and then there'll be a power gud here. Yeah, or coming off pin 1. But if you look at this chip here, you'll see it has 23, 24 pins probably. Maybe one underneath it. I can see up to 23 anyway. Now let's have a look at the chip on our board. This is the buck regulator coil that has the 0.8 volt supply. And we can see right by it, this chip here, AEAE064. Now if you look at this chip, and this is definitely the controller for this buck converter, this buck regulator. If you look at this chip, you will see that it has 5 pins down each of 2 sides and another 2 pins on the other side. So this is only a 14 pin, maybe some underneath it. But it doesn't have 24 pins, so this cannot match the one on that schematic. But it must be doing the same sort of thing. So this must have an enable because it is working, and it must have coming out of it a power gud. So we need to see on this chip where the power gud is. And the way to do that is to find the data sheet. So you can see the part number AEAE. This is not actually a part number, this is an SMD code, and from this we need to work out the part number. We'll search for SMD code AE. I actually know what this is because it's a very common one. I've come across this many times. SMD code AE. And this has got a few links, but we're going to go to this one, S manuals. And down here you'll see AE and the various package types. SOT23, 89, etc. And if you look down here, AEAE, AEA, and I'm sure we'll actually find the one we want. Yeah, there. AEA followed by some other letter. QFN16 3 times 3, and this is actually our package. This is the part number NB671GQ, and I know this one well because I keep them in stock. It's a very common one, and it's worth keeping these in stock, by the way. Hit the download, and this is the thing, and you can see there the pin out, and I'm sure, yeah, this is the diagram. 5 pins either side, 2 and 2, and there were 2 more underneath it. And look, top marking AEA. So we know this is the one on our board. What we're interested to know is which pin has the power gud. There, PG. That one. That will be the pin that is sending the signal out. I mean, this is, I think, just like a test application where we're just looking at a typical application, so it doesn't show it going to anywhere, but it will do. It will go to the enable on the next voltage rail to power up, which we know is the memory supply. So we need to look at what's on this pin to see if it is high. I know it's active high because if it was active low, it would have like a line across it, or a star or hash in front of it or behind it. Although I'm sure the data sheet, if we look through, will actually tell us. PG. Power gud output pin is open drain signal is high if the voltage output is higher than 95% of the nominal. So there we go. We know it's active high. And it's pin 4. Here's our chip, and there's a dot here. So this is anti-clockwise. It's always anti-clockwise. Pin 1, 2, 3, 4. And I'm sure you can see that pin 4 actually goes to this resistor here. Yeah. So we got from here. I'll just put it onto resistance range. You'll see it quite clearly. There we go. Yeah, bleeps as well. So pin 4. I'll use the microscope and we can just make sure. I'm sure I can see it actually goes to here. Well, it looked like it went to here. Yeah, it goes to there. So that's the enable signal. So it's easy for us to test on the resistor to see if we have an enable signal on our card. You can just check on the supply, 0.89 volt, and we'll just go on to the resistor and let's have it to see what we have. And it's low. Is the supply still on? Yeah, that's on. But the enable signal is low. What's on the other end of this resistor, out of interest? Ah, so that's a 5 volts. That's like a pull-up or something. But we have a no enable signal, even though the chip is working. That suggests we have a problem with this chip. Is it my imagination? Or does the solder around this chip look particularly shiny? And does this end of this resistor also look like maybe some of these bit that with a soldering iron? And Lewis and Albero, this card that you sold, had it had any previous work done on it? And be honest about that. Or had it never been worked on? Because this looks to me like this has had some work done here. And this is where the fault is showing. Let's just have a think about this then. So we have on this board, we know that on the 3.3 volt supply we have a low resistance, and this isn't normal, 13 ohms, and we know basically that goes to the EEPROM because we've measured it to the EEPROM, and we know it goes to the GPU from a circuit diagram of a similar board. So we basically know where that goes to. This is the EEPROM. There it goes there. I had a look around all the capacitors on here and I couldn't find where it went, but I'm sure it does go to there. This voltage rail, which I think is PEX, is running, but the power good signal isn't coming out of it. Now, I have here a similar board. This is an R9390. It's not the same, but I'm sure you can see that this part is the same. So this is the same chip as the one on here. They're identical chips. AEA. Same chip. NB671, I think it was. Let's have a look at the comparison on this one, because it's similar. Okay, it's a different GPU, but it's a kind of a similar layout. And I think this is more typical. So if we go on here to 1, 2, 3, 4. Yes, I just have to switch the auto ranging off. Sometimes it does that. And we can see I'm on kilo ohms now. So we can see we've got like 350 ohms on here where we got 14 on the other one. So that pretty much tells us straight away there's probably a fault in this GPU on this one. This, which looks like it's probably PEX on here, is reading 220 ohms. On this one, it's reading 45 ohms, so much lower. I'm going to power this board up and let's have a look around this chip, because we know this voltage rail is running. We can have a look at the power good coming off this one, and again let's compare it with the other one. On this R9390X, and by the way, this isn't working. This is actually the topic of another video I'm working on at the moment. But this area of the circuit is working, so we can have a look. We can just switch it on, and we can see on this one, we have 0.96 on PEX, yeah? And on the resistor, this is the power good, same as the one we were looking at. We have 5 volts. So we have 5 volts on both ends. I'll just go to the other end of the resistor. There, yeah. So we have 5 volts on both ends. On our board, the RX480, we have 5 volts on one end and nothing, 0 on the other end, which is wrong. On this board then, the RX480, I'll just power up again, and we have 0.89 896, so lower voltage on here. And we have, and it's just switched itself off, which it has a habit of doing. Switch it back on again. We have 5 volt on one end of the resistor, and we have 0.05 on the other end of the resistor. Now we need to just figure out why that is. And I'm just going to show you now something that probably confuses people, especially beginners, because you probably think that the power good signal comes out of this chip, like this chip sends 3 volts or 5 volts out as a power good. And that's probably because people like myself say, oh, we've got 5 volts coming out of this chip on power good. Well, that isn't actually quite what happens. So I'm just going to show you how the power good works, and then we can have a look to see if we can figure out what's wrong with this one. Here we can see the data sheet again for the NB671, or the AEA as it is marked. And we can see we have PG, power good, and it's connected via a 100k resistor to VCC. And if we look a little bit further down, we'll find the pin description. So VCC is an internal 5 volts low dropout regulator output. So there's a regulator inside the chip that generates the VCC 5 volts. The power actually comes in on this V in. So the in pin supplies the power to the internal MOSFET, and the regulator operates from 5 to 22 volts. So probably we have 12 volts going in here, and then this should have 5 volts on as generated by the chip. And in fact we do actually have 5 volts on one end of the resistor if our circuit is the same as this. So we probably do have the 5 volts VCC. Now power good PG, power good output. The output of this pin is an open drain signal, okay? And it's high if the voltage, output voltage is higher than 95% of the nominal voltage. So basically, if we have the correct voltage coming out, which I'll show you in a little bit how it knows if it's correct, then this goes high. But I just need to explain probably for some of the beginners what this open drain signal actually means. Basically, this means that in our chip NB671, we have this power good output, PG. And inside the chip, this actually goes to the drain of a MOSFET. And the other end of the MOSFET, internally, is connecting to ground. Okay? And the logic of this chip can switch the MOSFET on and off. And this is what it means by open drain. It's just the drain of a MOSFET. There's no connection internally from here to 5 volts or to anything else. So the chip cannot actually put 5 volts on this pin, or 3.3 for a different type. Anything with open drain, depending whatever voltage is coming out on the power good, the chip itself cannot put the voltage on there. Instead, it has from here a resistor to 5 volts in this case, and this pin is actually connecting to VCC. And VCC, as I've just shown you, is actually from a voltage regulator, what's called an LDO, low dropout. And this has coming into the chip, V in 12 volts. So this 5 volts, as I showed you, is generated by the chip. That powers the resistor. Although it could be powered, this could be connected to 5 volts coming from anywhere. It doesn't have to be done this way. And all the chip can actually do is turn this MOSFET on or off. When the voltage output is not up to its rated level, this MOSFET is turned on. So the chip actually holds this point down to ground. Yeah. Once the regulator is running and the output voltage is correct or within 5%, it switches this off. So when this is switched off, it's basically not there, and it's this resistor that pulls the voltage up. This is called a pull-up resistor. It's very common, you find a lot of them, and that's how a pull-up actually works. So it's this resistor that is giving you the power good signal. not the MOSFET. Now, in our case, this is low. And there's a few possible reasons for this. One, this MOSFET short circuit. Okay, so the MOSFET short circuit inside the chip, we have a short from here to ground, and therefore it can never go high. But we can test that, we can check from here to ground. Two, this resistor has gone open circuit, so there's nothing to pull it up. It might have 5 volts on one end, but because the resistor is open circuit, there's no volts here, or almost no volts. So this can never go up, even when this is switched off. This can't pull up to 5 volts. PG cannot go high. That's the second reason. The third reason is going to be because the logic says the output voltage is not high enough. Now let me explain to you how it knows when the output voltage is correct. Let's take another look at the datasheet. So in the features it's telling us two things that are important. One, the output is adjustable from 0.604 volts to 5.5. So it can be anywhere adjusted between those. And two, it mentions that there is a 1% reference voltage internal in the chip. And this is important, and I'll show you now how it works. We have here a pin called FB feedback, and you can see that's monitoring the output voltage using two resistors, and it's the values of these resistors that sets the output voltage. But still, how does a chip know when it's correct? Well, it knows that using the reference voltage. So we can see here FB feedback, an external resistor divider to ground from the output. We've seen that, yeah. That's how it monitors the output of the regulator. But it has to compare that with something to know it's correct. And what it compares it with is the reference voltage, which I shall just scroll down and we can see. There we go. So this is our chip. Here's the feedback pin coming into what's called an operational amplifier inside the chip. And there's a 0.6 volt reference. So basically, when there's 0.6 volts on here, which matches the reference, it then knows the output voltage is correct. If there's more than 0.6 volts on here, it knows the output voltage is too high and reduces the on time for the high side MOSFET, therefore the output voltage drops. If there's less than 0.6 on here, again it knows there's too low a voltage on the output, and it now increases the duty cycle of the high side MOSFET to put a little bit more voltage into the buck regulator, the output. So that's how it does it. So those two resistors will be chosen, the values, such that whatever the output voltage is, 5 volts, 1.8 volts, 0.9 volts, there will be 0.6 volts on here. And this we can check for. And I'll just show you again on the piece of paper how that's done. We can add to our diagram now. So we know we have internally in this chip, we have ref, voltage reference, 0.6 volts. And that is coming in to this logic. And we also have coming in FB feedback. This logic also drives the high side and low side MOSFETs, which are internal, and that connects to a pin called switch SW, and that drives the coil. And the other side of the coil is V out, the output voltage, and we have from here capacitor to ground, or capacitors to ground. Now it works, as we know, by monitoring this voltage and comparing it with this voltage. So if, for example, we wanted 0.6 volts out, which is the lowest voltage this chip can actually give us, NB671, then we would connect directly from here to feedback. And when this is 0.6, it matches that. They're both 0.6. And at that point, the chip knows it has the correct voltage output. Power good goes high, and the high side and low side MOSFETs are controlled in such a way to maintain the voltage here to equal this. But we probably want more. I mean, in our case, it's 0.9 volt. And to do that, we actually use a resistor divider. So from here, we connect two resistors to ground. A bit of a scraggly resistor, that one, but there it is. Now, for example, if these resistors are the same value, say this one was 50k and this one was 50k, they're both 50k. This is a voltage divider, so the voltage here will be half the voltage here. They're equal, so it divides by half. So if we now connect this to FB, then the voltage here will be 0.6 when the voltage here is 1.2, and we get 1.2 volts out. Again, the two compare, they're the same, power good goes high, and the MOSFETs are switched such that the voltage stays stable. That's how it works. If you wanted 1.8 volts, then basically you would make this one to 100k, leave this at 50. So this is now twice of this one, so twice the voltage drop on this one as that one. So this now would have 0.6 volts across it, this would have 1.2 volts across it, and this would be 1.8 volts. And again, this sees 0.6. This always sees 0.6 as being the correct voltage, regardless of what the output is. This means, for example, if the values of these resistors have changed or they're wrong, this will give you the wrong output voltage because the ratio of the two resistors is wrong. But this will still stabilise when it's at 0.6 and it will still give you a power good. So it's not a situation that the output voltage is wrong, therefore the power good doesn't come on. This doesn't know what the voltage is. All this knows is that this is 0.6 and this is 0.6. And of course, depends on the two resistors. So that's how it should all work anyway. 0.6, 0.6, power good goes high, and that goes to the enable of the next stage. And that's what's not happening on ours. So now we know this, we can look again at our chip. We can look to see what's on the FB pin, is it 0.6? And while we're at it, let's just check a few other things as well. We can see now, feedback, 0.6, it should be. Enable should be high. We're pretty sure that's high because this thing's actually giving some output. But let's check. And VCC, which is internally referenced, should be 5 volts if the chip is working correctly. So let's check VCC for 5 volts, feedback for 0.6 volts, enable for high, probably 5, could be 3.3. Let's check all of those to see what we have on our chip. While we're at it, we may as well also check this one, V out, which is used to sense the output voltage. So it should be connected directly to the coil. So that should have the same voltage that's coming out of our buck regulator. And we may as well just check V in to make sure. I mean, this should be between 5 and 22. It's probably 12. So we'll check those two as well. And that gives us, I think, everything we need to test on this chip. We've done the groundwork. This is the chip. I've just drawn it out so we know which pin is where. This is the dot for pin 1 on the chip, so we know the orientation. And we know which pins have the signals we're interested in, and we know exactly what voltage we should find on them. We do know this one is wrong, but when we measure the voltages now, because we've done the work, we're not going to poke around aimlessly on this chip just seeing what's there. We know what we're looking for. Yeah, we have a purpose. We know what we're looking for on each of these pins, so we can measure all these, make a note of the voltage readings, and then from that information we can make a diagnosis of what is wrong in our circuit. Let's look now to see where we can easily measure these. So we know already that on R794 is power good. V out is the pin at the end of the chip just here, and that should just go to the coil. I'll just measure the resistance. Yeah, that goes to the coil, so that will read whatever's on the coil, so we can measure that on the coil. So I'll just make a note of that. V in, V out we can measure on the coil. What else do we have? We have V in, which is 12 volts. V in comes in on, I'll just use the microscope. V in is here, okay, and it probably goes to these capacitors. Yeah, so we can measure V in here on the capacitor. I'll just make a note of that. So that's on C320. VCC is on, yeah, I can see on my diagram. I'll show you where VCC is. So VCC is on the second one up here. This is VCC. It probably goes to one of these capacitors. Yeah, so we can measure VCC here on the end of C5026. I'll just make a note of that one. C5026. And then we want FB. FB feedback. That's on, oh, the next pin. Okay, so that's on the middle one on this side. This is FB. And this will go to some resistors somewhere. Let's see if we just figure out where it actually goes to. I can see a couple of resistors here. Doesn't go to there. Maybe I wasn't on it. This is a low value, won't be that one. It might be these. Yeah. So that goes to the little resistor here, or 755. That's where we can measure FB. Or 755. And the last one we want to check is EN, which looks like it goes to a little via. So this is the EN pin coming in here. And there's a little via. I've just scraped away at it slightly. Yeah. So this little via here, this is where we can measure the enable signal. So let's power this up now and let's just check all these signals. First one, VN. I'll just, yeah, you can see that, VN. So VN we know was on the end of C320, which is here. So we can just power this up, and this should have 12 volts. Yeah, we got 12 volts on that. The other one, VCC, was on the end of CO526, this one. And that's 5.12, that's close enough. The next one would be enable, which is on the little via, and because the thing is basically running or giving some voltage out, this must be correct. But let's just get into the microscope and let's have a look. So this should be high on this via. What have we got? Yeah, 3.3. So that's high. That's good. V out just is whatever's on the coil. 0.896. I'll just make a note of that one. So the next one is going to be feedback, FB. This should be 0.6. So I'll just power it back up again. Just get into the microscope so we can have a quick look. So FB is here. What we got? There's something wrong there, yeah. There's something wrong with the feedback. Okay. So that should be 0.6 and it's not 0.6. I've just switched the power back off again to double check this. But we seem to have a problem with the feedback circuit, which kind of makes sense because if the feedback circuit isn't working, this chip will not think there's any output voltage and therefore the power grid won't go high. So once again, middle pin definitely goes to here. So we can just check this once more, but I'm confident we don't have any feedback voltage. I'll just get onto the point and I'll switch it on. So I'm on the end of the resistor. Let's switch it on. Let's see what we've got. Put it on to volts again. Power on. Start. Oh, now we do have. I must have had a bad connection. Okay, so we got 0.6 on there. Yeah, and the last one then is power good. So power good is over on this resistor here. And power good is low. So that suggests that this should be working. The fact I have the 0.6 here really settles it. There we go. Yeah, 0.609. Why don't we have any power good? I mean, we checked this before, and I'll just check again. We'll put it back on. So on the resistor, the pull-up resistor, this end has 5 volts, 5.12, which is exactly what we saw on the VCC coming out of here. So that must be where it does go to. So either now this resistor is open circuit, or there's a short circuit from here to ground, or there's something not right with this chip. Well, the first one is fairly easy to check. Is there a problem with the resistor? I mean, on the example circuit, it said it was a 100k, but I suspect it's probably something like a 10k. But let's have a look so we can actually just go across the resistor. Let's get my glasses so I can see what the reading says. One moment. 9.96k. I mean, that's so close to 10 as makes you think this must actually be a 10. So the port resistor's okay. Second one, have we got a short from here to ground? Well, there's a little bit of voltage on it, so I wouldn't say we got a short. But have we got a low resistance from here to ground? Let's have a look. One moment, is that reading meg or was it reading k? Yeah, that's reading 1 mega ohm. That's 1 mega ohm. So there's not a high resistance. I mean, if this was reading maybe like 1k, it's a voltage divider, and this couldn't go above about 0.5, but it's reading mega ohms. So there's no short in the chip. There's no problem with the resistor. There's no short wherever that power good is going to. So it would suggest there's a problem with this chip, although I must have to say that's quite an unusual fault, but all the evidence says that we have a problem with the chip, and the only answer now to that is to change it. I thought I had these chips in stock, but I don't have. I would have to order. But I'm just gonna try just tidy up the soldering on this side. It looks a little bit messy. It might be where I was probing. And it looks like it's been soldered by somebody to me. It looks like somebody's changed this. And I'm going to remove it and then refit it again, just in case maybe they haven't got it soldered down right, so that I have the voltage on the feedback pin but it's not getting into the chip itself, something like that. Because I'm not totally convinced this chip's faulty. It's such a strange failure mode. It doesn't kind of sit well with me that it would fail in that way. I'm not saying never, but it just doesn't doesn't sit well with me. So I'm going to remove this, clean up all the pads and resolder it, and let's just see if it makes any difference. I've done that. It looks quite a bit better now actually than it did before. We can just zoom down a little bit and have a good look at it. So it actually looks better than previous. Yeah, you can see like solder on all the pads, which is how it should look, to be quite honest. Just focus, there you go. So let's try this again now and let's see if it made any difference at all to it. Let's have another look. Mostly I'm just interested in power good. That's the first thing I want to check. So I'm on the end of the resistor for power good. We're in volts range. Let's see what we've got. Well, it came up and went down. That was interesting. Something's changed. Just switch it off again. It kind of looks like it's trying to come up and go down now. What's on the output? 0.895 as before. This chip's not getting warm or anything like that. Power good. Off. Yeah, you see it sort of like comes up again. It's kind of like maybe whatever this is going to is where the problem is. So something is pulling this back down, and it might not be this chip. I mean, everything seems to be okay on this chip, but that power good goes somewhere, and I'm wondering if this is pushing it high and there's a problem where it's going to that's possibly dragging it back low, which would be the next voltage rail to come up, which is VMEM, which I'm pretty sure is this one. So let's see if we can find the controller for this one. Although I suspect because we don't see any short or anything from it, it reads like 1 meg to ground. They've tested that, so it's not like we're going to find a short over here, I wouldn't have thought. Unless maybe it goes through like some low value resistor on the way, transistor. Okay, let's see if we can figure out where this goes to, because I'm still not convinced this chip is faulty. The only other option would be to change the chip, and that means to order a chip, and I'm happy to do that, but I just don't think I'm quite there yet. I've traced where that goes to, not how it gets there, but where it goes to, and that's actually to this buck regulator, and this one is the one that has like 30 ohms or so to ground resistance. So this is actually VMEM, the one above the main V core over here. This one, I'm pretty sure this is the memory controller, and this is the core, the multi-phase. So I'm sure it's this one for 2 reasons. One, because the resistance of this is right for Samsung memory basically, and 2, because I can actually see where the signal goes. So we have this chip here, APW8, let's just get it into focus, this one, yeah, APW8722A. So if you look at the data sheet for this one, here we have it. So you'll see on the pin description, there isn't exactly an EN pin, but this one, comp, is actually the enable. So it says it's a multiplex pin, so it has that means it has different functions. So during soft start, it represents the output of the error amplifier, so it's to do with the regulation control. Pulling comp low, less than 0.4 volts, will shut down the controller. So basically this also acts as an enable. So basically if you take this low, it will disable the buck controller. We can see it's pin 7. I'll just scroll up and you'll see, because this is a standard SOIC, small outline integrated circuit, SOIC, and it's pin 7. So we can have a look on pin 7 of this one and see what's happening here. Pin 1 is here by the dot, so we always go anti-clockwise, 1 2 3 4 5 6 7 8. So pin 7 is actually here. So we'll go on to there. I'll just connect to ground. I'll just try to get the meter lead onto ground, so I've got one hand free. That should do it. And if I switch this on, you can see what oops, I've slipped. But if I switch this on now, no, I've not slipped. You can see what's happening here. So see, it goes high and then low. So we know this is basically connected to the other one. So this is effectively the enable coming from the power good on the 0.9 volt supply. Once again, I'll just switch it on. High, low, okay. So that's the other reason I know it goes there, because that's what's happening. I need to order some parts, but I just want to show you the 2 possible things that I can think of that's actually causing the problem on this card. Now bear in mind, this doesn't exactly match our PCB, and I don't have a schematic or a board view for this one, but you can see it's similar in some ways. So this adds the different chip to ours, generating the PEX. It calls it 0.8 on this, but it's actually 0.9 in my opinion, but this calls it 0.8. This is generating the actual supply line, and this is the power good, and this signal 0.8V P good. And if we just search, Control F, and put it in here, we can search and we can find out where that actually goes to, and you can see it actually comes to this circuit here, and ours is going to be something similar to this but not necessarily the same. So the power good basically comes in here, and you can see there's a pull up to 3.3 volts. Ours has a pull up by the chip to 5 volts through another 10k. This circuit, from how I see it, is either this voltage has to be high or this voltage has to be high. Either of them being high will turn this transistor on via this resistor. This turns on, pulling this voltage low, turning this one off, and this therefore goes high, and this is MVDD comp. This is the enable, and I'll show you in a minute. For this to be switched on originally, either of these voltages needs to be present, either 12 volt buzz, I'm pretty sure that's just a 12 volt, or this one, MVDD source. I'm not sure where it comes from, I won't bother to look. But basically, for this transistor to turn on, therefore holding this enable low, keeping the RAM supply off, either of these needs to be on, either or both, and this needs to be off. Now I'm just going to print this out so I can show you what might be happening on our card. I'll also just show you where this signal goes to this MVDD_COM. So we'll just copy that and we'll just paste it into here. Okay, so we can now see where that actually goes to. Give it a moment. Sometimes my browser kind of like locks up a little bit with data sheets. Yeah, so it's here. So you can see that that signal comes into the comp enable pin on this chip. Again, it's different from our chip, but it's a similar type of thing. And if you look, this actually has some signals to it, driving upper gate, MVDD upper gate. There'll be an MVDD lower gate somewhere there, yeah. And they go to here loop. So these are actually your MOSFETs, one high side, two low side, and generating the MVDD, which is the RAM supply, 1.35 volts, I would think, on this card. So we know that signal is doing basically what it should do. On our board, this is going on and off, and this is going high and low because the 0.8 volt power grid is going high and low. And that's the question is now, why? One happy haircut later, I can tell you what I think about this. So this signal here coming in, this is the 0.8 volt power grid, 0.8 V P grid. So this has to be high to turn this transistor on, okay? Or this one has to be high, either of them being high. If you look at the value of the resistors, 10k, 10k, either of these being high would turn this transistor on. When this transistor turns on, it pulls the base of this one down and turns this one off, allowing the output to go high. And this is the MVDD enable signal. Comp it calls it, but that's the enable signal for the memory control, sorry, for the memory power supply. So that's how it works. Now a short circuit capacitor or something here would not cause this symptom we have where the power grid comes on and goes off again. The same with a short circuit transistor, it wouldn't do it in any way between power grid. If our circuit is like this one, there's quite high value resistors, so a short circuit here wouldn't do that. The best I can come up with is one of two possibilities. Either there's a problem, either our circuit actually has a MOSFET or a transistor here to ground, controlled by something else, yeah, which is kind of like an override. So if this goes high, this turns on and grounds this point, which would cause what we see to happen. So from here, this is going into our, let's draw it, this is going into our P grid coming out of the PEC supply, and internally on here we know we have a FET which can connect power grid to ground, or if the FET is switched off, this floats, and we've seen we have a resistor here to 5 volts, which is what pulls it high. So we know we have that. If you had, say, a MOSFET here that you could switch on, it would ground this point and it would pull it back low again. So you would possibly see this goes high, then an instant after this turns on for some reason and pulls it low. But I have no idea if that exists in our circuit. It's supposition. I don't have a schematic, I don't have a board view. If something like that doesn't exist, then the problem has got to be in this chip. I can't see any other reason why. It's got enable, the feedback has got 0.6 volts on, which is the same as voltage ref, 0.6 volts. So regardless of what voltage is coming out of it, this chip thinks it's right. Whether it should be 0.95 and there's some problem with the resistor divider that sets the voltage, this wouldn't know. This only knows what is on the feedback pin. through the two resistors, as we've looked at, and this should be 0.6 volts, and it is. And the internal reference is 0.6 volts. So all I can assume is there's something wrong inside here. I can't think of any other reason. Okay, so I'm going to order some of these chips. I'll just Alvaro, Lewis, you can see this. Let me know. I'll show you how much they are in a moment. I can order these chips. I thought I had them in stock. I don't. I have NB69 one, which is a different chip. I can order them. They're not very expensive if you're happy to pay the cost of the parts, which is like about €4 or something. Okay, if I then fix it, you can pay me the 45, which is what I quoted, and this will be fixed. Yeah, if I can't fix it, you pay for the parts. Okay, that's the first thing. Yeah, the second thing, we have about 12 ohms on 3.3 volt coming in. Yeah, now I've asked on the Discord, Learning Electronics Repair Discord, and the guy said, oh, I've got one of these cards. So I said, oh, can you measure this resistance, and can you also measure the resistance from here to ground as well? And he came back and he said that this to ground, 3.3 volts on the PCIe, was about 280 ohms. Notice how I use ohms and R interchangeable, by the way. They mean the same thing for you beginners. Yeah, if you see 280R, 280 ohms, it's the same thing. But he then went to say, I think, oh, you got 280 on yours, I've got 12. And then went to say, but my board doesn't have a GPU fitted, it's been removed. So his resistance readings are not going to help me. The only other reply I got on Discord was, before you mess around trying to trace this lot, change this chip. Okay? So taken from the horse's mouth, and the guys on the Discord, I'll go along with it. So let's order some of these. Let's fit that and let's see if power good comes on. If power good comes on, the rest of the voltage rails should come on. If all the voltage rails come on and it still doesn't work, there's a problem with the GPU, which there might well be, okay? But the only way to prove it, really, would be to try it. I mean, it is possible this 12 ohms resistance is being caused by something else, but it's certainly not stopping 3.3 volts from powering up, because this is drawing about 250 milliamps. It's not as short. The 3.3 volts is quite capable of supplying that. I don't know why it is so low, but I'm not familiar with these cards. Maybe that's just normal. Okay, so there you go, guys. This will have a part 2. Lewis and Alvaro. And I did say I'd show you how much. Hold on. So look forward to the part 2. Any comments on what else might cause this that I haven't thought of, in the comments below. Yeah. Any thoughts on this, in the comments below. Yeah. And on the final matter, which was the first matter, the backstory to this, I have to say, so far I can't come up with any definitive answer or proof as to why this was sold working and then came back not working. It certainly hasn't been butchered. This has not been, you know, destroyed by a monkey with a hot air gun. There's no shorts. This notwithstanding, there's some slight evidence that somebody's worked around the area where I'm working, which makes me think, well, if you're good enough to do that, why haven't you changed, or have you already changed this chip and it makes no difference? Is it the same card you sold? I don't know. Certainly nobody's sent you back a butchered item or something that wasn't what you sold to them. Other than that, yeah, guys, comments below. Interested to hear what you think. Yeah. And on that note, we'll call it an end for today. If the chips get ordered, we'll see what happens once they're here. And in the meantime, I'm sure I'll have lots of fun fixing other stuff. So that's the end of this video, and I'll see you all soon on another Learn Electronics Repair. Ciao for now, guys.